So what I'm going to do that, but I'm going to kind of put tracing in context in my debugging efforts. And what we'll see is it has a critically important, but not that large role. So it's something I wouldn't want to live without, but if it was disappear for a year, it'd be okay as long as it's back when I needed it. Kind of the way it works. Isn't that the way life is in a lot of ways? Okay, so that's the top thing I'm going to cover. I'm going to start with something I do fairly often, which is to present two definitions, which you can accept or reject as you like, but I'll make my position very clearly known on them, and the consequence. The two definitions, one is a definition of non-trivial software, okay? And my claim is that if you have a non-trivial piece of software, there's at least one bug in there somewhere. So, and put it another way, if you have a piece of bug-free software, it's clearly a trivial piece of software. One saving grace in all this is that the size of a trivial piece of software is increasing slowly but steadily through my career. So if you take a view in terms of decades, maybe things will work out, aside from the fact that it's getting more and more complex with time faster. A reliable software system pretty clearly has no known bugs. Because if there was a known bug, I mean, that clearly means there's some aspect of it that's unreliable, right? So if you take these two as given as I do, there's an inescapable consequence of the two of them. And that is that if you have any non-trivial, reliable piece of software, it must necessarily contain at least one bug that you don't know about. All right? And, well, I would argue that Linux-Kernel is fairly reliable, and my part of it as well. People keep telling me it's non-trivial, so there's at least some bugs in there I don't know about, and tracing is one way to find them. But nonetheless, it's necessary to find the bug, and again, tracing is one avenue. All right, but of course, it's even better not to have the bug in the software in the first place. All right, and there's, if you do software engineering and look at some of the things people like Capers-Jones has published. He shows a graph as you go through the different phases of software, right? And the further upstream you get rid of the bug, the cheaper it is. So if you can get rid of it during conceptual phase, if you have some stupid thing you're trying to do, I'll have an example of this later. Figuring that out up front and doing something smart instead of stupid saves you a huge amount of time and effort. On the other hand, if that gets out to the field, and so you have, in the case of Linux-Kernel, possibly millions of copies of this thing out there, getting rid of it is a real pain in the rear and very difficult and expensive. So you want to catch them as early as you can. And so I'm going to start before tracing, the design time if you can. As I said, it's best to do something smart than to do something stupid. Okay, to the extent possible, you want to establish the requirements. And this is always a problem because we never know really what they are. I had a dinner discussion with a formal verification academic earlier this year. And the guy had a really hard time with my statement that Linux-Kernel RCU's requirements are empirical. I mean, there's a few of them that are kind of sort of mathematical, and there's actually been a couple different mathematical expressions of them over the years. But, you know, if something shows up, maybe there's a bug in the kernel, and maybe that RCU is doing what I intended, but it could well be the best way to fix the bug is to change RCU. An example of this showed up a couple years ago, where there were these massive explosions during boot time and some hangs. So the system would just kind of hang at sometime in boot. It turned out what was happening was people were posting RCU callbacks before RCU init was called, before I was even initialized, way, way early in boot. It wasn't like they were trying to do this intentionally. They just added an RCU callback, a call RCU, to some common code that happened one way or another to be called really early. Now, one reaction would be to tell them, look, get your act together. RCU doesn't do that. Fix your freaking code, which would be one position, except that it was a lot harder for them to do that than for me to rework the callbacks in RCU to make it so we could tolerate that kind of behavior. So that meant that this was a requirement I would not have anticipated. Why would anybody do call RCU before RCU init time, right? I mean, that's before anything. The scheduler's not there, nothing's there. I mean, but it happens. So That's why there's this, to the extent possible. We learn about the requirements as people use our software. As people use it in unexpected ways, we learn more, and sometimes very surprising things. Another one is to understand the hardware and things underneath it. A real common problem we have with concurrency over the past 10 years is people have sort of made up what the requirements for concurrency are and program stuff that doesn't take into account certain physical laws, like the fact that the speed of light is finite and that atoms are non-zero in size, and therefore it takes time for information to propagate even inside a fairly small CPU. And if you do that, you'll end up with stuff that performs horribly, doesn't scale well. And people have done that over and over and over again over the past while. So if you take the time to learn, you don't have to learn all the details as long as you are content with 50, 60, 70, 80% of the performance. If you want 99% of the performance, then you're going to have to learn a huge amount about the very fine details of what the software, the hardware does. But if you're willing to take the easy, I don't know, 50 to 70%, depending on what you're doing, it can be 99% if you're doing something fairly simple that parallelizes easily, then knowing a little bit about the hardware will go a long ways. The other thing is take your design and set it down. Write the thing down, talk to people about it. Because if you don't do that, what happens is you look at this part and you say, okay, this is great, and you go to the next part and that's great, or the next part, and then under the unknowns, you know these funny 3D diagrams where they show something that doesn't make sense? You know, the people going up the stairway and the stairway just comes back in a loop even though it's going up all the time. You can make one of those in your head really easily because you're only looking at, if you look at it one stair at a time, it's just fine. So if you actually take the time to write the stuff down and record it, counterintuitive that may be at some point. Because, I mean, you know, right? What's the problem? Well, yeah, you look at one piece at a time, it's fine. That can really help. In some cases, formal verification at design time helps. Matthew and I have done that with reduced-based RCU. I did it going back in the early 90s. On the other hand, a large fraction of the time, not always, but a large fraction of the time, if I feel the need to apply formal verification at design time, that's a hint. And the hint is, McKenney, you're doing something too freaking complex, think about it harder. At least about 3/4 of the time, what's happened is a few years later, I've come up with a much simpler way of doing it that didn't really require the formal verification. Now, there are some things that happened recently where that hasn't happened, whether that means we just wait a couple of years and find some simpler way to do it, or that it's just really necessary in those cases. I don't know, we'll see. Okay, so that's design. And perhaps we do tracing and design, I don't know, but I'll leave that to Matthew and Dominique to work that out. We have to do coding. And it's really good to avoid bugs in coding. It's also really hard because the most natural thing in the world is just start typing stuff, feed it in there, and see what happens, right? And the problem with that approach, as with many other things, is that approach uses your own intelligence against you. The smarter you are, the bigger a hole you'll dig for yourself before you realize you're in trouble, all right? But don't take my word for it, find out for yourself. Anyway, one thing that helped me out was I used to use these things. My first paying job involved that. That's actually a class from back in the late 70s somewhere, I think. That's a assembly language from a CDC 6600 follow-on, Cyber 73. And the thing about those things is that if you're lucky, you take a deck of those and hand them to some operators, and in a few minutes you get back some printout. If things are all busy, it's going to be some number of hours, and if things are really busy, it may be a day or two. Or worse. So in this, if you have a certain period of time, like a week, to get the assignment done, and your turnaround time might be measured in days, you're going to work pretty hard to try to get the stuff taken care of. And what that usually involves is writing the code down by hand. That ends up being also a good review process. Unfortunately, as we've seen in Linux-Kernel, there's 10,000 eyes make all lunch shallow, but good luck getting 10,000 eyes on your piece of code, all right? And especially good luck getting 10,000 informed eyes on your piece of bug, informed in the particular specialty your code happens to be in, right? Inspection worked really, really well when I was a student because I was doing business accounting programs, and everybody knew about numbers and that money wasn't supposed to get bigger or smaller through the process, and the time was supposed to elapse. So it worked pretty well, but ever since then, in networking and in memory allocation and so on, not so good. Anyway, so what I am doing, and I did this with punch cards as well, you write the code down on a piece of paper. You correct bugs as you go. You do this in pen, always in pen, never pencil, okay? Because pencils have erasers, and that breaks the further steps. Okay, what happens then is if you've had made any corrections, you copy it on a piece of paper in pen, and you read that until the last two copies are identical. One benefit of this is that it really rewards writing short code, because you don't have to write it out so many times. Now, you don't do this for everything. Clearly, if you're just writing, just doing a grep or something like that, it doesn't make sense, because you can just type it and it'll blow up if it's got a problem. So you don't do this for not complex code. And there's a fine line between the two, and you'll always fool yourself and decide it's not complex when it is, but life's like that. There's one rule of thumb: it's definitely not complex and it's sequential, and you can type it line at a time in an interpreter or something and see what happens. Then you can do trial and error line by line and maybe get it right. So this is an example from RCU. It's the infamous RCU prepped offline tasks function. And that was my first attempt. As you can see, things didn't go very well. So you start over, right? And things were a little bit better on this copy. I still had to go back and correct a few things. And finally, the next thing, it was the same representation. I mean, the lines were in correct order instead of kind of with arrows in them, but they're the same. So, okay, it's time to type it in and see what happens. Next question is, how well did I do? This is the patch I submitted. The red lines, can you see those? Yeah, look at that. We have a projector, we can see red. Maybe that's not such a good thing, but okay. And all I really did was add some more nuances, which, okay, fine. I'll forgive myself that. The line 25 and 26 I interchanged. It makes absolutely no sense to have done that. I don't know why I did. I mean, if you assume that there was going to be ordering, you'd want it in that order, but it's under a lock and there's no ordering. But okay, so I interchanged the lines. So that's not too bad. But of course, we have maintenance as a process over time. And so a couple years later, we ended up with that. And what happened was that there was a higher level design issue, and I needed to know whether there had been any readers that were moved. What this thing is doing is it's moving preempted readers up the RCU node tree, okay? And so I needed to know whether any had been actually moved, so I added rect file and set it up and then returned it. Okay, still not so bad. That was fine until a year or two ago, and I ended up with that. Yeah, I've done a good job pointing it, but I was doing something stupid, all right? Why are we moving the things at all, right? Just leave them where they were. And if you do that, there's a whole bunch of races you don't have to have. But what's happening is CPUs are going offline. If all the CPUs corresponding to a given leaf node are gone offline, then you want the tasks that were preempted on one of those CPUs to be still waited for, right? You don't want to just ignore them after that. And what I was doing before was moving to the root so that they would always be looked at. Okay, that meant I had to move them. There was a time when they were sort of not anywhere, and I had to get two locks, and it ended up not working. Leave them where they were. And then just have the grace period mechanism be a little smarter and actually look at, not just say, oh, there's no CPUs on this node, so ignore it. No, there are no CPUs and there are no block tasks in this node, then we can ignore it. And then it's much simpler, it doesn't have the bugs, and life's better. So this is an example of a whole bunch of work that happened that should have just not happened at all. I should have been smart enough to begin with to realize I didn't need to move the stupid things, but okay, here we are. Okay, the thing is, and I should have put more effort into design, clearly, in retrospect. But at some point, you got to start coding. I mean, you can think about the stupid thing forever and not get anything done. And depending on the situation, at some point you have to say, I know what I know now, I'm going to take my best guess, and I'm going to deal with the consequences of the mistakes I'm going to make based on my complete knowledge. All right. Another thing is that, sometimes speed counts. If you got a critical bug and it's killing people, you might not want to spend several days scrawling paper. Some of you might get upset about that. After all, you've got a problem right now, and it's not like it's great and you can break it. It's like it's broken. Can we make it better, right? Can we kill fewer people? Would be a good step forward. Although I prefer not killing people to begin with. The thing is, though, you have to follow up with the complete process. Okay, stop the bleeding, get things taken care of, and then look at it carefully and go through the full process again. Of course, the problem is once you get it to where it looks like it's working and the bleeding stopped, it's, God, let's go for a beer, right? And then forget about the second step. And there was a case in 2009 where I was doing RCU for the first time, where I fixed a bug and didn't follow up, and then ended up I didn't spend a couple of days to follow up, and as a result, about 6 months later, I spent the better part of a month tracking down the resulting bug and fixing it. So, it's taking a long-term view doesn't pay off in the short term, but it sure can in the long term. And by the way, who's responsible for taking a long-term view on the bugs? Yeah, you can blame management. That feels great at the time, but you're the one that's going to be under the gun fixing the thing when it's broken, not them. I mean, sure, their boss will be yelling at them, but they'll just turn around and yell at you, so it's no problem for them. If you can't take a long-term view yourself, sorry. I would strongly suggest leave the blame and management game to Dilbert cartoons. At the end of the day, we're the ones actually doing the work. They have the authority, we have the power. We're actually pushing the buttons, making things happen. By the way, it's a good trick to align with whatever management initiatives, shall we call them, happen to be around at the same time. A couple of years ago, people were excited about Agile, so whatever you need to do, make sure that it's, if they say, but we got to be Agile here, so whatever it is they're using, right? If they give you an easy way out, take it. Come on. Okay, so I did all this and there's still bugs. Well, that's neat. I mean, I do all this and I still have bugs. It is a real world out there, and Murphy is very active. And the point is that what we're trying to do here is reduce risk. You have to balance reducing the risk of producing the code with the risk of not having the code. All right? So, no matter what you do, there's going to be some problems. At some point in your career, you don't have the choice of not being yelled at. The choice you have is what you get yelled at about. Okay? And if you think about that earlier rather than later, it makes things simpler. All right, do I want to get yelled at because I got things done quickly and had a whole pile of bugs and then get yelled at for a long time fixing the bugs? Or would I rather get yelled at for a short period of time while I'm doing it right and then not have the bugs? I mean, you'll still get yelled at, there'll still be some bugs left over, but that's the kind of choice you have to make. But anyway, testing is another point of reducing risk. And the point here is up to this point, we've been trying to not have the bugs in the first place. In this case, we've got the bugs, they're there. We're human, error is human, we'll make mistakes. We want to make them show up as quickly as we can so we can fix them. And there's a bunch of stuff. My personal favorite is, of course, RCU torture, but a bunch of people have done a bunch of stuff. They've done great work. And, the kernel still has bugs, but in, 2000, maybe as late as 2011 or 2012, if I wanted to do RCU torture testing, I had to wait till -RC2, 3 or -RC4. If I tried -RC1, it was exploding for whatever reason, and I just couldn't do any meaningful testing. It was great to test then and to report the bugs, but I couldn't actually test RCU meaningfully. For the last, 3 or 4 years now, I've been able to go with RC1 almost all the time. Maybe 2 or 3 times over that time where I've had to go to RC2 because there was some bug in the way. So these things have made a big difference. and I've contributed my little piece, but you know, we should give a hand to Dave Jones and Yo-Fung Wu and Stephen Rothwell and whoever else for a lot of the work they do, which isn't necessarily the most glorious work, but it's made a huge difference. Okay, but you know, it'd be good to take a look at some example bugs and see what the needs are, I guess. This is a famous one that Thomas and Peter might remember from 3.0. Showed up very late in the process. But the problem we have is that RCU relies on the scheduler to schedule its k-threads. And the scheduler uses RCU. And so clearly, if you're not careful, this can cause problems. Anyway, I'm not going through this in detail. There's a LN article that I wrote about the whole sorry story. But what happened was we had changes in RCU, in the scheduler, and in the interrupt handlers that worked fine independently, but had a really low probability bug of taken together. The fix was in RCU, so I guess I get to take the blame. But it was a weird thing where you'd be returning from interrupt while you would be getting out of RCU restart critical section, you'd take an interrupt, you'd have been preempted at just that point in time, and RCU would forget it was in the restart critical section, and life would be very hard thereafter. The fix was fairly straightforward. RCU has now I'm in a restart critical section, and I'm getting out of a restart critical section, and I'm not in a restart critical section state. That's three separate states, and that avoids the problem. It also motivated me to get QEMU running on my laptop because by the time we found out what the problem was, I was in Nanjing. I figured out, oh, I know how to fix this. I immediately got on a high-speed train to Shanghai. High-speed train is really cool. If you haven't been on when I suggested, it's really impressive. But it didn't have Wi-Fi back then. That night I couldn't get at my testing farm. And I sure as heck wasn't going to take my only working piece of computer and try running a new RCU on it, a native. And I didn't have access to the internet, so I couldn't figure out how the heck to make KVM and QEMU work. And so I sweated bullets for 2 hours looking at this stupid thing over and over and over again. When I got to Shanghai, I had about that much time on Wi-Fi before I got on the plane to like some of the patch. And fortunately it worked, but I don't like living that way, so I now can debug on my laptop with KVM. Okay, so this was bulkhead by normal testing. There was only 2 machines in the world that found it. A couple PCs, we don't know why those were different headed, but they did. Another one was this thing. I'm not going to go through this in detail, but as you see, you have to have, if you have default configuration, you need at least 17 CPUs, and at least 3 of them doing something special at just the wrong time. This was in production for 5 years. And as far as I know, it didn't trigger. Yeah, it didn't like me for some reason. Okay, let's try this again. LibreOffice decided it just had enough of this. Okay, let's do that one. And yeah, sure, I'll recover. Why not? All right. This is great. It's like when it has 2 copies of open, which doesn't sound like it's going to be all that great of a deal at some point. You know, I think I'm with somebody earlier this week that said you should use VI for your presentations.
Yeah.
Okay. Okay, now we seem to be okay more or less right now. Let's try this and see if something useful happens.
You probably found another bug here.
I probably did.
So you're saying you can press electrical?
Apparently not. Not reliable either. Okay, so anyway, this was and the problem was, I'm not going to go through this in detail, but because RCU needs to scale well, It can't force full agreement across the all the CPUs on when things happen. And so different CPUs have different ideas when the grace periods begin or end. And that offset could, through some rather strange but quite possible sequence of events, cause a grace period to be too short with respect to one of the readers. Turns out it's fairly easy to fix. You do that instead. Everybody still disagrees on when things start and end, but they do agree that the one grace period ends before the next one starts, okay? And that's sufficient to prevent the bug. This was not found by testing. I found it when I was trying to make another change to RCU, and it exploded after I changed it. And then it was like, why did this ever work? And it's kind of like, oh, well, I guess it never did, and we got lucky. And these weren't trivial 5 years. I mean, we had machines running up to 4,096 CPUs working just fine with this bug there. And both of these bugs, by the way, weren't things that depend on memory ordering. Both of them would be bugs, even if neither the compiler nor the CPU ever reordered anything. All right, so they were kind of in some sense straightforward bugs. But so clearly, continued improvement in testing and validation is needed. One reason, a few years ago, I realized that there are more than 1 billion instances of Linux in the world today, and maybe 2, I don't know how many it is, because you got 1.4 billion smartphones, they say. There's like 80, let's see here, so we've got 80 million servers. Lord knows how many household appliances there are, and who knows what's going to happen with the Internet of Things, whether we use Linux at all, or whether it'll be mostly some trivial OS, but it'll probably be some one and some of the other. And the problem with this is that, well, even if you only have 1 billion, let's suppose I have a bug in RCU that happens once every 1 million years of machine time. That thing's happening 3 times a day across the installed base, all right? And that is not necessarily easy to test for. Now, it turns out, oddly enough, that if I assume the old style smartphone mode, somebody that actually uses a smartphone mostly to make phone calls, as opposed to people that are chasing Pokemon or texting forever, which admittedly is a new thing, and I'm going to have to deal with that. But let me live in the past for a little bit, okay? If I have it turns out that if you assume that there are people making phone calls 1% of the time, when the thing is doing something, it's spending 10% of its time in the kernel, which is kind of high, but okay, let's be conservative. If the kernel is spending more than 1% of its time doing RCU, people start screaming at me, so I think I can assume that for an upper bound. And RCU bugs are mostly races, so you have to have 2 of them, which gives me a factor of 10 to the 10th. There's only 10 to the 9 smartphones out there, right? And at that point, also they tend to have a small number of CPUs, like just on larger systems. If you throw all that together, I could do 7.9 days of testing. Actually, I can reduce that, but let's keep it simple. And I can say I put as much stress on RCU as 1 billion smartphones does for a year. So that's kind of cool because I can actually fit 7.9 days in a 60-day release cycle, sort of. I obviously can't have very many test failures, so I don't get very many instances of 7.9 days in a 60-day release cycle. So the servers are much worse, and the reason is that they're utilized much more heavily. And so I need 29 years per release cycle. It's kind of tough to fit 29 years of testing in 60 days. I mean, you can do it, you just have to have a huge number of machines. The problem is, if I did that, I'd be spending all my time keeping the machines running, probably more than all my time keeping machines running. I wouldn't be able to do anything. So that's clearly infeasible. So, what are we going to do about this? One approach I could take is to say that how many people have a smartphone that they could be running for 1 million years from now? No optimism in the crowd? Jeez. What is it, sunless Germany, everybody's depressed? I don't know. So that's one way of doing it. One thing is that there's a bunch of dirty tricks I've been doing, and I know how to do over 25 years to make the failure conditions happen more rapidly in my tests than they happen in real life. Do lots of CPU hot plug operations, for example, and a bunch of other things like that. And I can also target test because I know kind of where some of the race conditions are, at least the ones I know. But this is actually, I have to advance my state of the art in testing to really be able to say that I'm testing RCU well enough for its current environment. Okay, but let's set that aside. And what do I do once a bug is triggered, this is where we finally get to tracing. Well, the usual thing, this is really tough on the ego, but it's pretty productive. What did I just change? You know, because whatever you just changed is probably what caused the problem if you're doing unit testing and so on. But this is surprisingly difficult. There was a LKML exchange over several weeks that kind of proved that point recently. I won't name names. Chopping commits up into smaller pieces, so you can, because the thing is that analyzing a piece of code in kind of the general case, in kind of the usual case, I should say, grows exponentially with the lines of code. So the more you chop your code up, if you get bisect to a given patch, you have less work to look at that patch. And that happens, I'll do a patch and it'll blow up in RCU torture and it's like, I don't know what's wrong here. If I chop it up into 5 or 10 pieces, it's slow. Yeah, this is obviously wrong, and you can fix it. Another thing that's been productive for me is to look at where the thing happens. I've got 16 scenarios in RCU torture, and usually a failure will cause 1 or 2 of them to break and not the other ones. At that point, I can look at, okay, what are the config options? What am I doing in those ones? And say, oh, well, it has to be this piece of code. And then, again, that focuses me down and I have a chance of analyzing it. Debug print Ks and war-nons are quite valuable, especially if I can make it so they're only executed once I know there's a failure. If I have to execute them all the time, well, the common case bug in RCU is a Eisen bug. That's one of the reasons why tracing is so far down here. I mean, the other one is pulling the user space and apply the code and stuff there. Because tracing has a small but real effect on timing. And it's reasonably likely to change the behavior. Nonetheless, if I've done all this and I can't do it, tracing is a good option. And if we have time, we'll talk about formal verification as well. I don't think we will at this point, but it's what it goes. Okay, I mentioned that. So when can I use tracing? And these are some examples where I can. Grace period latencies. Grace periods are measured in tens of milliseconds often, and tracing is clearly not a problem there, right? No, you just go ahead and do it. In fact, there's a thing called RCU perf. It's kind of a companion to RCU torture for performance. And what it does is, I've got scripts I run. I just type a command and it goes off and does the 16 things, and I can type a command and it can do some RCU perf stuff as well. What will happen is it'll fire off some KVMSs using QEMU. It'll run them. I guess I should leave that. It also builds the kernel. I should put that in there too. Collects the console log. And then what happens is that the first script in that list is in the main line. You can look at it if you want. It calls the second script. The second script looks for ftrace information. If it finds that it analyzes it using that, if not, it says, sorry, I ain't got none. And then the top little script uses some D-message output that the test puts to do the analysis. So this is something, if I'm doing performance analysis, I use tracing, and mostly event tracing in this case, and that's there. Another thing is if I have non-Heisenberg grace period computation, which sometimes happens, and I do have some scripts for this, but they're old and crufty and they won't see the light of day until the same bug happens often enough that the same script can actually work more than once, which so far hasn't been the case. The other one is where something doesn't happen. If something doesn't happen, it's really hard to figure out where I'm putting the debug printfs and the war-nons because it didn't happen, right? And in that case, I'm going to have to do something like tracing, and often what happens is that it does decrease the probability because it changes the timing, and I just have to use really long runs. You know, sometimes, tens of hours or days even to make the thing reproduce in that situation. And also come with a very large trace output. And another one is if you just want to see what RCU is doing, in which case, well, it can do a number of things, and it could do something slowly rather than quickly. I mean, slowly, the traces overhead is very small, actually, it's pretty good. But nonetheless, if you're just looking for what it does, you can just turn that trace on, look at the functions, and see what it does. And Frederick Weisbecker did this about 5 years ago and actually found some places where it was unnecessarily doing things twice. It wasn't harmful, but it was certainly confusing and unnecessary. So we patched that up. Okay, so my worst story for today involves injected bugs. I won't get time to talk about it, but one thing that's really cool that's happened in the last few months is 3 separate groups have taken automated formal verification tools and done verifications in significant portions of Linux-Kernel RCU. Right? Now I keep torturing because they didn't find any bugs. I know there's bugs in there somewhere. But, so what I had to do was I had to give them the bugs. You know, here's a buggy RCU, can your tool find the bug? And that's kind of I don't like that as well because they can just diff and see where the bug is and then, you know, but at some point you have to, at least they didn't say printf verified as their total verification thing. At least you know that, right? At least they had to have two programs and choose among them. The other thing I do is have them give me the stuff so I can run it. Although in one case, one of the tools makes a logic expression. In the bug-empty case, it was tens of gigabytes of logic expression. And it took a stat solver 84 hours to punch through the thing and find the problem, so I'm not going to run that one. Anyway, one thing that was kind of surprising on one of them was that RCU torture located the bug itself in all the scenarios you'd expect except for one of them, this 301 scenario. And it said, oh, just fine. Now it wasn't a killer problem because, I mean, 305 certainly screamed about it at a rate of some large number per minute. But still, it's a little bit surprising that you have this buggy thing and in one scenario says, whatever. So the thing was that what the bug did was when the CPU came in and said, do what it would do is say, oh yeah, I do need to do something, there's a new grace period, I need to respond to it. It would clear out all the other CPU's bits, which would essentially say, yeah, these other CPUs are done, even though they weren't. And what that should do, what you'd expect that to do, is to make it so that occasionally you'd have two short grace periods, which certainly was happening in the other scenarios, a lot. Therefore, RCU should complain. But it wasn't. Now, one of the things unusual about 301 is its tree is one node. And so one of the failure cases that can't happen is where all the bits get cleared out in one node, and everybody says, oh, we're done here. And then the bits in the upper level nodes never get cleared as a result because nobody bothers going up to the next level. And that was, in fact, one of the failure cases that was happening a lot in the other scenarios. One red herring was that 301 enables preemption, so I was looking at preempt RCU, but I eventually said, oh, let me check what it's really testing. It was the bottom half variant. So the thing is that, so what I did was I did some tracing, and let's see if I can do this. I'll get the right one here. All right, and we have this one first. So I'll make it so you might have a chance of reading this thing. And let's try pushing it over here and see if you can see it when I do that. Look at that. Okay. Now let's see if I go full screen with the thing. Okay, this is the trace output from it, and I've annotated it. And let's see here. Yeah, look at that. I'm still typing at it. No, that's not right. I don't want that. There we are. And so what we've got going on, the grace period started. There's a start there. CPU start means that a CPU noticed there was a grace period. This is a CPU that actually started the grace period, so it noticed pretty quickly, obviously. And so it did there. It noticed it. It cleared all the other bits. And then a bunch of other stuff happened. We had scheduled clock interrupts happening through here. And so at this point, only CPU's bit is remaining set. CPU 7 comes along and it clears everybody else's bits. So at this point, all the bits are cleared. And at that point, bad things could happen. Okay, except that in this case they didn't. Had they done so, the thing would have complained. Let's see here. Yeah. So we go down and we have more scheduled clock interrupts, more stuff happening, and eventually, keep going down, we had a forced advance of state. And that makes what SOTA is doing is going and looking to see if CPUs are idle. But the thing is, that was 3 milliseconds later. The probability of having a restart critical section extending for 3 milliseconds. I mean, RCU torture does make them happen, but it has to do it fairly rarely, otherwise you'd only have long RCU critical sections, and you would be testing fast ones. And so, as a result, by the time it got there, all the readers were done just naturally, And at that point I said, oh, everything's 0, and then the grace period was done, and things worked by accident. At this point, I think I'm at the end, pretty close to the end. The next step, obviously, is to put tracing in to find the guys that are long, so I can find them and look at what happens around them, but that's an exercise for later. Anyway, at this point, if people have questions, I'll take them. And if not, we'll go to the next speaker. Got one in the back, then. I guess over here, but I can't see behind the post.
Thanks for your talk.
Very
Very interesting. And I'm wondering if you've considered using hardware trace units which don't have this overhead.
I've considered it. The problem is that you have to know a lot about the problem to set the trace up. And I could potentially use the x86 or PowerPC debug registers to try to find stuff. But my luck with that in past attempts has not been that good because they're limited resources and I usually need to wait for something fairly complicated. And I just haven't, but to be honest with you, I haven't looked in the last, 10, 15 years because I got some down on a previous attempt. Maybe I should look again, I don't know. Other questions? That's a question. Okay, thank you for your time and attention, and go to the next speaker.